Welcome back to the Hyperbolic Coding Chamber. We are recruiting and the HCC needs you. You should join the HCC. Why? Because we have hundreds of thousands of members joining every day. Why? Because we have commandeered the resources of all the top tech companies and poured it into our Discord server. So that's another reason you should join. So things have been going well in the Hyperbolic Coding Chamber. There's been lots of chats recently about how to get better, what resources, things of that nature. So if you're interested in those talks, you should join. Fortunately, we have some comments to stall us before we must enter our scheduled suffering for the day. So if we take a quick look, we'll see that we have some legendary comments from Evan Howlett. Very cool profile picture. I hate the questions like the first one. Oh wait, my mic is very far. I hate the questions like the first one. Like, I want to see an algorithm or use case for something like this. Good job though. Hey, feel strong, man. Yeah, I don't remember what the first question was. I think I was literally just checking this. My computer is being very ghetto. So if we just check real quick, what are we peeping here? I think it was decode something. Yeah, it was decode something. So, yeah, does that question have to be stopped? Yes. Yeah, there's some problems that we get given on LeetCode that just don't quite make any sense. I guess the whole point of it is to follow a particular thing, like some instructions or something like that. But sometimes it's just weird, or it just doesn't feel like it's an elegant solution, or it just feels like you're doing something just for the sake of doing it. But maybe that's how things work. I mean, largely, the decision tree we have in our brains is made through repetition, maybe. So I'm not certain, but yeah, that problem, at least it's another thing we'll be able to stomp down later on if we run into it. From Raul Does Nothing, legendary computer toucher, also writer and gardener. The whole intro really captivated me. Great job. Feels strong, man. Facts, bruv. Feels strong, man. I don't actually remember what I was talking about. Feels strong, man. Yeah, I don't actually remember what I'm talking about because most of the time I'm just saying what's come to my mind. So I think I went with the quote and just kind of kept going. But that was, I think, yeah, that was interesting. But yeah, I mean, we got to show up. So the daily grind, I think I'm proud that we made the decision recently. Not perfectly, of course. We've been trying to stick much closer. I used to vary the time a lot, but I realized that made it very difficult. I think that was a very useful skill in the beginning, to vary how much time I allowed myself to do. I think later on it became kind of troublesome. I'm not turning off that ability because it's just too useful. Some days you really just have to do a recovery run. So some days I do bring down the time. But recently, for the majority, I don't want to make any hard and fast rules, but recently the majority of the time we've spent has been a solid 1 hour, with occasional times, shortened lengths for like, in case things like family stuff comes up, or work stuff, or I'm spending a lot of time at work, or like overtime or something like that, or just general woes of the mental kind. So yeah, I think that's been a really good change. So it's been really useful to see how that's come about, because we've been able to solve more problems more frequently. I don't know how long this will continue, because like Michael Scott says in The Office, I wish there was a way to know when you're in the good times. So we might be in the good times right now in terms of problem solving, where things are working out. We're able to do like between 4 to 7 problems a day just in an hour, but they're just all easies. Maybe we're in the good times, but the good times inevitably end. And maybe we'll run back into the easies where we're spending like 30 minutes or something like that, or just spending the whole thing on an hour. But it's been kind of cool to see the pace pick up recently. So hopefully that keeps up so we can get over with the easies. I'd like to go to the mediums now, but I did say that we would finish the easies first and then go to the mediums. And I kind of want to stick to the things that that plan that we set. Because I think currently we're at 282 done, 234 out of 607. Let me see. We have 282 done. Most of them are easy. Most of the mediums I did during, I think it was prep for a big tech interview. That was a little while ago. But yeah, hopefully we can do all those. Then we can just go to mediums. But yeah, I remember when we first switched over, the whole point was that the hards are. I was doing. I think I was just kind of doing whatever. I was doing like some medium, some easy, but I think I was running into an issue because I was struggling a lot on the medium problems, but also I was struggling to show up. So since I was struggling to show up, also struggling as hard as I did on the exercise in general was just really difficult. I guess an analogy would be, it was hard to show up to the gym, but I would show up to the gym and then still try and deadlift 900 pounds. So it was just like I was making it too hard. I should have. What ended up happening is I dialed up the difficulty of the stuff back, modulated the difficulty of the workout so that mostly I was practicing showing up, which was really useful because now it feels easier to show up again. Before it was getting really questionable. Not questionable, but it was just really difficult. So obviously we can't stay in this space forever. I think we're starting to master the 1 hour time block. I don't want to speak too early. There's always things that come up. So we're mastering the hour block and showing up. So I do feel like we're only 1/3 of the way through the easies. I'd just be really curious to see how we would be at the end of the easies. So setting a medium term goal, having done all the easies, it would be really cool to see what kind of programmer. I mean, I wouldn't be like pumping through websites or anything, but it'd be interesting to see what kind of like problem solver we'd be by then, and also if we've extracted anything new. So that being said, the HCC needs you because we don't know what we're going to do for a couple of decisions, and one way to make sure that we make good decisions and we don't ruin the guests we have scheduled, because last week we had Adam Sandler, we had Drake, we had tons of popular celebrities giving us talks. So if you would like to have a voice in choosing the next person to join the Discord and give a talk on a programming topic, you should definitely join, because that's where we're doing the voting. So you might catch me, Elon, maybe a couple of other big tech executives, maybe some other known names just shooting shop about about tech and keyboards and whatnot and else in LeetCode. So you should definitely join for that. And yeah, I think we're about ready to jump into it. We're gonna do the standard hour, and hopefully we'll be able to continue the progress. So here we are. Oh yeah, we used to do the weekly contest, and we stopped doing that. So that's kind of a feels bad, man. We used to do the weekly contest, and we stopped doing that. So that is unfortunate. Should we return to the weekly contest? It's a good way to keep things rolling. We'll see. If we remember, I wouldn't mind doing it like we were doing it weekly, but I always forget, and then we forget to do it, and then it's a whole thing. So I'm just gonna we already have some problems loaded up. So we're gonna begin with a mathy problem, it seems, today. Great common divisor of strings. For two strings S and T, we say T. Oh, for two strings S and T, we say T divides S if and only if T divides S if and only if S is equal to T plus ... plus T. T is concatenated with itself one or more times. Given two strings, string 1 and string 2 return the largest string X. Given two strings string 1 and string 2, return the largest string x such that x divides both string 1 and string 2. For two strings s and t, we say that t divides s if and only if s is equal to t plus dot dot dot. T is concatenated with itself one or more times. Given two strings, string 1 and string 2, return the largest string x. Between two strings, string 1 and string 2, return the largest string x such that x divides both string 1 and string 2. So you have string 1 and string 2, return the largest string x such that x divides both string 1 and string 2. It looks like we're looking for the longest string such that, so if, for example, if we pretend that s is 4 and t is 12, the greatest common divisor would be a number x such that x divides both 4 and 12, and that number would be 4. And I think we're looking for the same thing here, but in terms of strings. So you have string 1 ABC and string 2 ABC. The greatest common divisor here is ABC. Here we have AB, 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 and the greatest common divisor here is AB, because this has 6 ABs, has 3 ABs, and this has 2. And what they share here is 1. This is an interesting problem, but it seems like it might be a bit harder than it initially perceived. Maybe the beginning, well, what if we thought of this? What if we did the GCD of two numbers and then tried to morph it into the GCD of two strings? The way we do the GCD of two numbers, we would just we would start with the smallest number, because the greatest common divisor can't be greater than the smallest number. For example, if we're trying to get the GCD of 12 and 6, the GCD can't be 12 because the smallest number is 6. So the value has to be less than 6. Start at the smallest number, and we could just check. The problem with this version is that for an arbitrarily large string, this would be very, very bad. But for 1,000 strings, for 1,000 character strings, it might not be the worst. Seems like the first thing might be to check that both strings, I guess we'll jot some ideas down. GCD of num2string, or intuit cheat code. Maybe there's a simple solution that we can intuit if we think about the problem a bit more. It feels on some level that we might have to do some prefixing, because what if the strings don't have the same prefix? Because these two strings don't have any shared prefix. Since they don't have any shared prefix, they simply cannot be divided by each other. I'd also like to see if something like ABC For example, if we change case 1 from ABC, ABC to ABCD, is the answer still ABC? We return an empty string. The output, or the expected output is AB now. Oh, no. I have to go to case 1. The expected output is, wait, expected is empty. Interesting. So a substring, right, because it has to be the string repeated. And ABC, the answer isn't ABC because you can't form ABC by repeat. You can't form ABCD by repeating ABC a bunch of times. So you could write a longest common prefix algorithm. How would that help us? If we were longest common prefix algorithm, we would get ABC, ABC, it feels like you already have to do the GCD. For example, if you have something like ABC, ABC, right? Let me fix this test case. If you go back to ABC, right? The greatest common divisor's length, or the length of the pattern that can repeat, can at longest be the length of the shortest string. That would be ABC. And then from ABC, there's only one. Can the repeating pattern just be A? It does say that string 1 and string 2 can be of length 1. So it means that the greatest common divisor here can either be 3 or 1. Right? Because the length of string 1 is 6 and the length of string 2 is 3. Which means that if there is some length of a pattern that can be repeated for both string 1 and string 2, it must be, if we treat them as numbers instead, the length of the pattern must be the greatest common divisor shared by the length of the strings. So we have 6 and 3, and the greatest common divisor starting from the smallest length string would be 3 or 1, which means the pattern length can only be 3 or 1. We know from the answer the pattern length is ABC. And from this one, for example, with AB, 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 we have 6 and 4. The greatest common divisors of 6 and 4 are 2 or 1. So the pattern is either 1 character long or 2 characters long, and we can check those. at the end of the day, I think what they're really asking for is the pattern itself. Seems like they're asking for the pattern. So what we could do to solve it is potential patterns. Figure out potential pattern lengths, then try them to see if they work. If none work, return empty string, I think is what we could try. So we could try that to figure out the potential pattern lengths. We just do the GCD of the smallest and I want to say if we write a function, right, GCD of, it wouldn't be GCD. I'm expecting potential lengths to be the length of an array or have multiple elements. If we had a function called GCD, get GCD, it should return a singular number. Unless we're writing a function called get common divisors. So maybe we should just choose the greatest common divisor. Is there a scenario where it doesn't make sense to choose the greatest common divisor? In this case of 6 and 3, the greatest common divisor here is 3. We could have also chosen 1. But if the string was all A, and they're both all A's, there's actually 2 answers, A, as well as A, which is a singular A. And then it still works that you could choose the greatest common divisor, which would be triple A's. Here we have 6 and 4, the greatest common divisor here being 2. We can check if that works with A, B, and it does work. Here with 4 and 4, the greatest common divisor would be 4, and we can see that the letters don't match at all. So this not, I guess we should just get GCD of string 1 string 2 dot length. So we'll just call this GCD num, and we'll take num1, which is a number, and num2, which is also a number, and then return a number. How do we get the GCD? Well, we have to figure out which one's the smallest and the largest, because we want to choose the smallest one. So largest would be equal to if num1 is greater than num2, right? Then largest would be num1. Otherwise, it would be num2. And we can create smallest, because if largest is equal to num1, right? Then smallest must be num2. Otherwise, it must be num1. Then for smallest, right, we'll say while smallest is less than or equal to 1, we're going to say if num1 mod smallest equals 0 and num2 mod smallest equals 0, then we want to return smallest. I think this should give us the GCD, but let's test the ideas. Let's test the idea here. And if when we make it out, we shouldn't make it out. I mean, we'll just return 1. You shouldn't make it out of this while loop, just because 1 is always a common greatest common divisor unless the numbers are 0. And even then, if you did 0 mod 1, yeah, you'd still get 1. So you should never make it out without returning 1. But anyways, if let's say we passed in 6 and 4, 6 is greater than 4, so largest is 6, and smallest would be 4. Largest is equal to 6, so smallest must be 4, otherwise it must be 6. Smallest is 4. And what we want to say is actually that smallest is greater than or equal to 1. And we'll say if num1 mod smallest, which would be 6, 6 mod 4 equals 0, it doesn't. And 4 mod 4 equals 0, it does. Well, we'll just subtract 1. 3 is not going to work. Then we get to 2. 2 does give you a remainder of 0 for both, so we can return 2 as the GCD. From here, check pattern actually exists. And then for that, we'll start with I is equal to the shortest string. So we'll say shortest equals string 1 dot length is less than string 2 dot length. The shortest string then would be string 1, otherwise it would be string 2. You only need to check the shortest string because, actually no, we need to check both. Because you could have a test case like this where you have AB, AB, AB. You finish checking the short string, right? So you check AB pairs here, but the end string looks like this. And they actually don't divide. So I think what we want to do instead is we'll just have string 1 index equals 0 and string 2 index equals 0, and we'll just say while string 1 index is less than string 1 dot length or string 2 index, or string 2 index is less than string 2 dot length. What we'll do is just make sure that the pattern repeats for both. So to do that, to get the pattern, we could say pattern is equal to either of the strings should work. So we can just say string 1 dot substring 0 and GCD num. To get the pattern, then we'll have pattern index and we'll say if string 1 sub string 1 index does not equal pattern sub pattern index, right, we're going to return an empty string. We're going to do the same thing for string 2. Otherwise, right, we're going to increment the pattern index. So to do that, we'll just say if pattern index equals pattern dot length, we'll set it back to 0. Otherwise, we'll set it equal to pattern index plus 1. And there's one more thing I think we need to add, and that is string 1 index is less than string 1 dot. I think we're almost done. I think there's one last thing I need to think about. So if there's still room left to go in either of them, we should keep going. We don't want to do any out of bound checks. So stir2 index is less than stir2.length. We still need to increment these indexes. Stir1 index plus equal 1. You can duplicate it. So I'm just going to click run and see what happens. So it fails. So I'm going to print GCD num. We're getting 3, which is good, which means pattern should also be good. Right, so now I'm not exactly seeing what's going wrong here. String one if string. At a brief stint, let me see. I think that made sense. I think it was going out of bounds on the pattern. So it looks like that does work. It feels like this would be n plus m time, or the max of whichever string is longer. But I'm a little skeptical on how long this GCD function takes. But since the strings are limited to 1,000, might not be the worst thing in the world. So this person says S1 plus S2 is return if they equal each other. If S1 plus S2 oh, that's pretty clever. But how do we know? That's really clever. So if we had ABC and ABC, ABC, if you do ABC plus that, you get ABC, ABC, ABC. Otherwise, you'd get the other way. You get ABC, ABC, ABC. Now, if that is true, then you just need to take the GCD of the size, which is basically what I did. Did they not? I guess Java just has a GCD function. That's really clever. Yeah, that's really clever. That is really clever. That is a really clever problem and a really clever solution. Given the root of a binary tree. Given the root of a binary tree with unique values and the values of two different nodes. Given the root of a binary tree with unique values and the values of two different nodes of the tree X and Y, return true if the nodes corresponding to the values X and Y in the tree are cousins, or false otherwise. Two nodes of a binary tree are cousins if they have the same depth with different parents. They don't have, so note that in a binary tree the root node is at the depth 0 and the children of each depth k node are at the depth k plus 1. So those here 2 and 3 are cousin. No. If we had another node here, so 4 and 3 are not cousins, 4 and 5 are cousins. I think we can solve this. I have to use the bathroom so bad though. I'm about to poop my brains out. It seems like this could be solved. I just have to make sure I'm understanding. A cousin is two nodes of a binary tree are cousins if they have the same depth with different parents. Since the node is unique, it feels like this could be solved with a depth first search, where each node we push onto the queue is also pushed on with its parent. Oh, I have to use the bathroom so bad. I'm gonna use the bathroom real quick. We have returned, and we've expunged our bowels. It's kind of funny. This function is called isCousins. So I think I was on the toilet and I was thinking. And I don't think I was on the toilet for very long, or like 5 minutes. But it seems like we have two issues to solve. One is the problem of parenthood. Another is a problem of depth. Both of these can be solved with their respective Both of these can be solved with their respective styles. So parenthood, you can usually create a parent array using a DFS or a BFS, and depth is typically, I think it's more simply solved with BFS, but BFS is shared here for both of them, so it might just be simple to solve this problem with a BFS. Since if the nodes are cousins, they would have the same depth. Once we reach a level in a breadth first search, once we reach a level in a breadth first search, we know that the level is all the nodes. We know that we have all the nodes for that level. For example, by the time we get to processing 2 in a breadth first search, 3 is already in the queue, because for them to both be in the queue, we had to have already processed 1. Similarly, if we're at 4, we've already processed 2 and 3, because it works level by level. So what we could do is work through the BFS, right? And as soon as we find one of the nodes, right? As soon as we find one of the nodes, whether it's X or Y, right? There's 2 things we can check. We can check that one, that other node exists in the same level, which would be all the remaining nodes in the queue, and 2, that they have separate parents. If we can't find the node in the level, then they aren't cousins. And if they have the same parent, then they aren't cousins. So it seems like we're going to write a queue, which is we don't actually have access to a deck in JavaScript. We don't have access to a deck, unfortunately. So the queue operation is actually going to run in n squared time, but that's okay. It's going to start with the queue, and we're going to say while queue dot length does not equal 0, right? I'm going to move some of the space back, right? We're going to say node is going to be equal to queue dot shift, which is going to take a node off the front, right? And we're going to make sure not to add any nodes that don't have a null value. We're going to make sure to only add nodes to the queue that have a non-null value, is what I'm trying to say. Say if node dot left, right? Then we'll say queue dot push node dot left, right? Same thing with node dot right, right? Then we'll push it on. Otherwise, right, we have to do our checks to see, right, if we're in the correct depth, right? So if node dot val equals X or node dot val equals Y, right, then we're in the correct level, right? Which would mean that ideally, if we're cousins, our node should exist in this level of the tree. So the one thing we have to figure out, right, is which value we actually are at. So value found equal to if node dot val. So how do we figure this out? If node dot val equals X, value found was X. Otherwise, if node dot val, otherwise the value found was Y, right? Cousin we're searching for, right? If the value found was X, right, then the cousin we're searching for is Y, otherwise it's X. So the cousin we're searching for is the cousin we're searching for. So there's 2 ways we'll know if they don't exist, right? So we can say cousin is going to be equal to queue dot find, and we're going to search to the nodes. I'm going to say node dot val is equal to cousin searching for, right? Now if cousin doesn't exist, right, it wasn't found in this depth or this level, then we know that they aren't cousins, so we can return false. And I think we're returning a boolean here, right? If cousin does exist, then we have to check their parents. We actually don't know their parents. So the way we can fix that is by every node being a tuple in the queue. So we'll say queue is going to be an array of tree node. Tree node or null. And then when we started with root, what we're actually going to do is its parent is going to be null. Right, and now when we pull a node off of the queue, we can say parent, right, as well as node. And the parent, right, is going to be the current node, right? And then when we search through our queue, right, we're going to make sure, right, because we're going to have a tuple. We're going to make sure that tuple sub1 dot val is equal to the cousin we're searching for. We're going to say cousin parent, right, and cousin, right? Now, if cousin doesn't exist, then we're going to return false. And the other thing we're going to say, right, if we can return the cousin parent, which would be a node, dot val does not equal parent dot val, and we already figured out the depth issue. And so what's right, because if we don't find the node, it means they're not the same depth, right? At the same time, if their parents are the same, then they are cousins. Okay, this is not working. I think the other thing I'm realizing is that this should go after. Otherwise, we end up doing things beforehand. Wait, I'm pushing the wrong value on. Wait, I'm confused. If we pull a node off of the queue, this would be the node's parent. With node left and right, and the parent of that node would be node. So for 2 and 3, we're returning true. So we start with a null root, right? We pull root off of the tree, root off of the queue. We say if node.val equals x, no.val does not equal x or y because 1 does not equal 2 or 3. So then we say, okay, does its left and right children exist? They do, so we're going to push on 1 as its parent with 2 as its left child, and 1 as its parent with 3 as a left child. From there, we go back to the top, we take the next node off the queue, which would be 2. Now no.val equals x. 2 does equal 2. So which value did we find? Well, we'll say no.val equals x. We found x. What's the cousin we're searching for? If value found equals x, right, then the cousin we're searching for is y. Otherwise, it's x. So we're searching for y in this case. Now we're going to search through the remaining queue and say q.find for each tuple, which should be just 3 left. We'll say does 3, which is in the queue, dot val equals cousin searching for 3 does equal 3, right? So if not cousin, return false. Cousin does exist. Now we can just return whether or not cousin. They're cousins if their parents, I see. They're cousins if their parents' values aren't the same. So we should be exiting with false here, but we're not. Somehow we're returning with true. It probably has to do with some JavaScript thing. We'll say if cousin is null. Or it might even be simpler to say cousin tuple. We'll say if cousin tuple, if not cousin tuple, return false. And then we'll say cousin tuple sub 0, which is the parent. I'm not understanding how it's finding. Oh, I see the problem now. We're not processing this level by level. Right, because after we process 2, we push on left and right, and then we go to 3, and then we search through, and then I think there's an easy way to fix this. We end up pulling the nodes off level by level, but in the queue, we don't actually have a level that we're processing. The way to get the level that we want to process is actually we can add a null at the end so that we know when to stop. And the null at the end would mean that all the nodes have been pushed on, and we can now look through what remains in the queue. So if after we pull the first node off, we'd have a null, and with that null, we'd know it's time to check 2 and 3. Getting a little bit confused. Even with that, that would only tell us, with the null added, that we just finished a level. If we just finished a level, we need access to the previous level. Then we could rewrite all this to pretty much look through the previous level. This solution to do them all in one was a little nutty. I think we could have also just wrote the function to map the nodes to their parents, and then wrote the function to map the nodes to their depth, and then we could have just checked if they had different parents and had the same depth. But we'll finish this one anyway. I think we just need something like previous level, which is just going to be an array of tree nodes. So we also just keep track of our previous level, and then this is going to be an array like so. And then we'll know we'll have reached the end. Maybe the structuring was a little messy. We'll say if the node doesn't exist, and the node not existing should signify the end of a level. Right, so if the node doesn't exist, right, then we want to do some work, and then additionally we have one more thing to do. We have to set up the previous level. We take a node off of the queue. We have to do previous level dot push parent and node. So in this case, right, the queue starts with 1 and null. We process 1, we push 2 and 3 on, right? And then at the previous level we have 1, then we get null. So we say the node doesn't exist, our previous level is just 1. Then we can search through. But that doesn't make sense. That would just be n squared time. Not n squared. We'd be looking through every level twice, which doesn't make any sense. I think we should just write the original version. Time to cut our losses. We have 2 problems to solve. The parent and the depth. We'll create a parent call node to parent. It's just going to be a map that maps a number, right, to a number. We can just, all the nodes are unique. So we'll say new and then we're just going to say DFS root node to parent. At the same time, we also get the depth. I don't see why we couldn't. Let's just say node to parent. And it'll actually be a tuple. First one being the parent, or the first one being the depth, and the first one being the parent. And then at the end, we should just be able to return we should just have to say x parent does not equal y parent and x depth equals y depth. And we can just say DFS. It's going to take the node, which is a true node, or null, and it's going to take a map here and we'll say if the node, we're also going to have the depth, which is going to be a number. We're going to pass in 0. Now, if the node exists, also going to want to know pre, which is going to be tree node or null. And then I think with that we should be done. Obviously the previous parent of the root node is going to be null, so maybe it makes more sense to do it like this. So we're going to say map dot set node dot val to a tuple of the depth, like we said, it's going to be the depth to the parent. To the parent's number, right? Since it's possible pre won't exist, we're just going to set its parent to infinity. Then we'll go node dot left with the parent being this node, right? With the depth being depth plus 1. Passing in the map. We'll change this to node dot right. And we just check node to parent. So we have case 2 1's depth is 0, parent's infinity. 2's depth is 1. 3's depth is 1 with its parent being 1. 4's depth is 2 with its parent being 2. 5's depth is 2 with its parent being 3. How are we getting the wrong answer here? Two nodes are cousins if they have the same depth. Oh, I did not get. Well, okay, that's my bad. I think I see what the problem is. I'm putting in depth first and the parent afterwards. We should do something like this instead. Yeah, the first one we went through, it just got a little. We could have still solved it that way, but it would just been n squared time, because after we finish processing a level, we have to iterate through all the nodes in the previous level. You would have processed each level twice. Each level n time, or no, yeah, each level twice. So I guess would have still been linear time. So maybe that was fine. So I would say this is linear time, linear space on the stack for the DFS, but also linear space in represented by the parent array. Yeah, the other cool problem with the DFS is that you could do early stopping. So that's true. So I think that's a good place to stop.